Yeah, so welcome back. Sorry about the apparent bus strike this morning, which is why we're starting a bit late. So you remember yesterday I started giving a little crash course introduction to the Anderson impurity model. And to do that, I considered first an isolated one-level atom. And then I started doing this exercise, which is coupling this single-level atom to a bath which has only one state, which was taken here to be at zero energy. Okay, and the bath and the atom communicate through exchange of electrons. Okay, and so what I did very quickly is to diagonalize that problem and to discover that V is a singular perturbation that lifts the degeneracy of the ground state. So the degeneracy is lifted in such a way that the favored configuration is a triplet, is a singlet state, which has a wave function that looks like this. It's basically a large amplitude on the singlet, which is made out of putting one electron on the dot and one electron with antiparallel spin in the reservoir, right? Plus a small component of order, this eta is of order V over U, which introduces in the ground state wave function a component which has 0 charge on the dot and charge 2 on the dot. Okay? So there are two important messages here. The first message is that originally at V equals 0, we had a doubly degenerate ground state with a local moment that could be up or down. And branching on V lifted that degeneracy, and that local moment got screened out by the conduction electrons in the reservoir to form a local singlet. Okay, this has a name. This phenomenon has a name. It's called the Condor Effect. And what you've seen here is an extremely simplified description of the Condor Effect, which amounts to deal with the strong coupling limit of the Condor Effect, where you really bind a conduction electron to the local moment to form that singlet. Of course, originally, the Condor Effect is something that was described, I'll come back to it a little bit later on in the tutorial, was described from the beginning with a full continuum of states in the reservoir, which makes the problem dramatically more complicated because V is a singular perturbation. Okay? So that's the first phenomenon, screening of the local spin by the conduction electrons to form a singlet. The second important thing is that this was achieved here by including in the ground state wave function virtual transitions to states with 0 charge on the dot or charge 2 on the dot. And because now the ground state wave function is a superposition of charge states 1, 0, and 2, you can perhaps accept the notion that it will allow charge to flow freely through the device with maximal possible conductance 2 E squared over H. That's a very qualitative argument, but I think this makes it plausible. Okay? So again, this is a Mickey Mouse description of the Condor Effect, but I think it is really the strong coupling description that allows you to get at least part of the crucial physics, the singlet formation. Okay? Fortunately, it turns out that when you deal with the full continuum states in the reservoir, you need to set up a normalization group framework to do that. But the flow of the coupling is precisely to strong coupling, which means that what we are doing here is actually a correct zeroth order description of the physics. Okay, so the consequence of that, as I said, is that you can restore full conductance and destroy completely the Coulomb blockade in the local moment regime. And if you have a real quantum dot with several levels, it means that there should be some odd, even alternation of this phenomenon. And you see that this is what is observed indeed here in these experimental results. Here, the spin was presumably odd on the dot, and as you lower temperature, you destroy the Coulomb blockade. Here, the spin in this valley was presumably even on the dot, and as you increase temperature, you gradually open the Coulomb blockade gap. Here again, even, and so on. Okay? So the thing I want you to take home from this is that there is this Kondo screening of the local moment, and that V is into a singlet state, and that V is a singular perturbation. What this should do to the conduction electrons in turn, if we were having the setup of a magnetic impurity in the metal, is that some conduction electron creates the binds here to the spin and creates a singlet, and this makes that site a very powerful scatterer for the other conduction electrons. So as a result of that, there should be a pi/2 phase shift of the conduction electron wave, which will now have vanishing amplitude of the on the singlet state, because in order to put another conduction electron here, you need to break this singlet. Okay? So pi/2 phase shift just means that a wave that had a maximum amplitude on the impurity site must now be such that it has vanishing amplitude on the impurity site, which amounts to shift this wave by pi/2. Okay? That's the description of the strong coupling fixed point. Okay. So as I said, all this is very singular in V, and if you want to deal, maybe I'll come back to this later, if you want to deal with this from the, let me maybe show this, where did I put, yes. If you want to deal with this for a full conduction electron reservoir with a continuum set of conduction electron states, what you need to do, well, the best way to do that is actually to eliminate these virtual charge 0, charge 2 states and derive an effective Hamiltonian that acts only on the low energy subspace of this singlet triplet stuff. And this can be done. It's called the Schrieffer-Wolff transformation. And what you end up with is an effective Hamiltonian, which is essentially the following. It contains my conduction electron reservoirs, and it contains a super exchange coupling between the spin on the dot and the conduction electron spin density at the impurity site. Okay? And this JK here can be worked out, and it's essentially something of order V square over U, which you can easily guess from the single site solution that I showed you before, because that's the energy, the typical energy that splits the singlet from the triplet. Okay, so forget this term, which is potential scattering. I don't want to discuss this. So this Hamiltonian is called the Kondo Hamiltonian, and if you actually take the problem from this perspective, which is the way people took the problem in the very beginning in the 60s, you may want to do some perturbation theory in J. If you start doing that, because J is nothing else than V square over U, not surprisingly, you run into difficulties in the perturbation theory because V is a singular perturbation. So in other words, when J is 0 here, we have a freely fluctuating local moment. As soon as a positive J is turned on, you will want to form a non-degenerate ground state, which is a more complex many-body ground state than the one I described before, but which is basically adiabatically connected to it, namely spin on the dot and conduction electron spin bind into a singlet state. To actually control the perturbation theory of this problem in J, you need to set up the renormalization group, and actually this is probably the first example of an application of the renormalization group to condensed matter physics ever. I think this is an accurate statement. The solution of this thing by Anderson, Yuval, and Hamann, and later Wilson, is actually essentially, I think, the first paper where an RG flow, so I'm not going to describe all this, I can keep this for the tutorial if you have questions, but I believe this RG flow of the Condor problem was actually the first time that an RG flow appeared in a condensed matter paper in the literature. Okay, so I've talked about the small v singular perturbation, but since we are dealing with the Anderson model in the first place, not with the low energy effective Condor model, we can take the problem from a different end. You can ask, what about dealing with this problem as an expansion in U? So from the weak coupling side. And this is what I want to focus on now. Okay, let me skip this and view the problem from the small u side. So the good news is that in contrast to the expansion in V or in J, which is very singular, the expansion in U is completely smooth. It's a completely smooth expansion, which with hindsight, you probably can guess, because this is a 4-fermion interaction, and we know that in many cases, a 4-fermion interaction is actually something that leads to Fermi liquid theory and doesn't break adiabatic connection. So that's what we can do. So let us first analyze the problem at u equals 0 and see how the structure of perturbation theory works out. So at u equals 0 now, this is the Anderson impurity problem. It is still a quadratic Hamiltonian, right? And because it's a quadratic Hamiltonian, I don't need to go to this oversimplified limit of only one conduction electron state. I can deal directly with a full conduction electron C. So here I've restored a full conduction electron C with all momenta. Okay? So it is a simple exercise to actually derive, for example, the Green's function for the creation operator of an electron on the dot. And this is written here. So those of you who like functional integration will recognize that this expression just comes from integrating out the C states from just a Gaussian integration, and you'll immediately get the result that you get the square of the linear coupling to the environment multiplied by the Green's function of the reservoir, which is 1 over I omega n minus epsilon k. So this formula gives you the inverse Green's function of the non-interacting Anderson impurity model for the creation operator on the dot or on the impurity. So you can look a little bit at this expression. This expression has two terms. This term is, of course, a very simple term. If this term was absent, we would just have a pole at epsilon d. But actually, this guy is really interesting. If we actually take the imaginary part of this thing, we get this, which is nothing but the expression of the Fermi golden rule that I mentioned before. So this is just telling me that the width of the level, because of the coupling to the bath, the level acquires now a width, a finite width, and this width is actually pi times the square of the transition matrix amplitude times the available states at energy epsilon k in the bath. Okay? So for, let's say, a very flat conduction electron bath and a V that wouldn't depend on k, this would be pi V squared density of states, which is what you expect for broadening that level by coupling to an environment. Okay. So let's now go on, and so that's what I was saying. You just get an I gamma, okay, from this continuous thing. So let me now go on and build the perturbation theory from this u equals 0 limit. One convenient way to do that is actually to continue with a perspective that focuses only on the dot degrees of freedom and integrate out completely the bath. This, of course, I can do even in the presence of interactions because the interaction term is only on the dot, right? And the coupling to the both degrees of freedom is just a quadratic coupling, VC dagger D. So I can perform this Gaussian integration over the C's, and what I get here is an effective action for the degrees of freedom on the dot, which involves, of course, now the many-body interaction U and a bare propagator, which is just the thing we derived. This GD0 minus 1 is exactly this expression here that I derived before. Okay? So what do we have? We have a theory of a local fermion. This is a zero-dimensional problem, plus, of course, time, which is I need to quantize the problem. And we have a vertex, which is just a 4-fermion vertex for opposite spins. So we just have a 4-fermion vertex. This would be spin up, this would be spin down with U. And we have a propagator, which is GD0 of tau minus tau prime. The price I had to pay for integrating out the both degrees of freedom is that this introduces retardation in this problem. So I have a many-body problem, which is zero-dimensional, but it's many-body all right. It has a local interaction, and it has a retarded propagator. Okay? Everything you know about many-body perturbation theory should apply, even in a simplest form, for this problem. In particular, when you work out what will control the way that interactions modify the Green's function or the single electron propagator, actually at low frequency, relies only on the way this quantity behaves at large time or low frequency. So how does that guy behave at large time or low frequency? Well, it's very simple. Because this guy has a finite density of states, so remember the imaginary part of GD0 was something like gamma over pi omega minus epsilon d square plus gamma square, something like this, okay? You see that at low frequency, this quantity is finite, which means that GD0 of tau minus tau prime for large tau minus tau prime behaves like 1 over tau minus tau prime. Right? This just comes from the fact that you take integral d omega of this quantity, which is the spectral function a d0 of omega, e to the minus omega tau. If this is finite at 0 frequency, this decays like 1 over tau. So now we can calculate the first order correction to the self-energy of the problem. I can introduce a self-energy, which is the difference between the inverse of the interacting Green's function and the bare Green's function in the absence of interaction. I guess you're all familiar with that. And I can calculate the first non-trivial graph. There is, of course, a Hartree term of order u that I'm not writing. You can calculate the first order non-trivial graph, which is second order in u. And just by power counting, this thing should be u square, 2 vertices, 3 propagators, so that's 1 over tau cube, right? The Fourier transform of 1 over tau cube is omega square. So this means that the imaginary part of the dot self-energy at low frequency behaves like omega square times u square times some dimension full number that will make this homogeneous to an energy. Okay? Which is actually the cube of the density of states at Fermi level of im GD0 at 0 energy. So this is rho d0 cube because I have 3 lines here. So this is 1 over energy cubed times energy to the 4th, which is indeed energy. Okay? So what is this? This is Fermi liquid theory, right? This is a local, very simple version of Fermi liquid theory, and I've shown this to you to lowest order, but this persists to all other in perturbation theories. So here you've seen that the only thing that the interactions are doing from this perspective is to build up a self-energy which will have a real part which is able to shift the position of my pole in the Green's function, and an imaginary part which will be at most of order omega squared at low frequency, right? So from the point of view of weak coupling perturbation theory, and actually to all others in U, there is no phase transition as function of U in this problem. To all others in U, we have a local description of the problem, which is a local Fermi liquid. So I can write then general equations. If you grant me that this is a local Fermi liquid, let me now write a general expression for the spectral function of the interacting problem on the dot or on the impurity side. So what do I have? My spectral function will be the bare one, which I just wrote here, modified by the real part of the self-energy, which shifts the position of the pole, and the imaginary part of the self-energy, which will provide a small correction to the level width gamma. Okay? And local Fermi liquid theory means that we know that the low frequency expansion of these quantities are of the following form. The real part, so now I've been a bit perverse here. The previous slides had imaginary Matsubara frequency. This one now has real frequency, right? Because we are discussing real things. So I focus on real frequency now, okay? Where physics is. So the real part of the self-energy has a regular expansion of the form constant plus linear term in omega. I've carefully called this term 1 minus 1 over z, you'll see why in a minute, plus so on, while the imaginary part has the characteristic form of a local Fermi liquid, and it starts like omega squared plus dot, dot, dot. Okay? So now let's put this in there and focus around omega equals 0. Just put this in there, do the math, this is what you get. So please observe this expression. It's very rich. It contains 3 important things. So the first thing is that this is a normalized Lorentzian, right? It integrates to 1 if I integrate over omega. So this quantity integrates to z. This is why here I was careful to put 1 minus 1 over z. This is the spectral weight present in the interacting spectral function close to 0 frequency, and it's equal to some number z. That is a microscopic number. We haven't calculated it. We know from perturbation theory that for small u, it's 1 minus something of order u square. At large u, it's something else, actually very small. Okay, now, the width of the resonance is renormalized also by z, right? And that's because here you need to pull out 1 z factor, and at the end of the day, this is what you get. The width of the resonance is of order z, z gamma. Okay, so the width of the peak was also renormalized by z. And finally, the position of the pole, this resonance, this spectral weight, is not centered exactly at 0. It's centered at a value epsilon d tilde, which is renormalized by the real part of the self-energy, but also by z. Okay? So let me focus in particular, so that you understand things without having to do any serious calculation. Let me focus in particular on the particle-hole symmetric case. In the particle-hole symmetric case, which is the center of that local moment plateau, where there is exact symmetry between the empty and the doubly occupied state, this spectral function must be even in frequency. So it must be, because of symmetry, that this epsilon d tilde is 0. Good, I can get rid of that guy. Okay? And so at the end of the day, in this particle-hole symmetric case, I just have one number, z, that I need to discuss. And I discover that my spectral function must contain a resonance at 0 frequency now, exactly at 0 frequency, because this is particle-hole symmetric, which has a width z gamma and a total spectral weight z. So this is really important, because what has happened is that we evolved somehow from a situation at u equals 0. I'm discussing the particle-hole symmetric case where epsilon d equals minus u over 2. Okay? So at u equals 0, this is 0. And we had the imaginary part of the Green's function for the non-interacting problem, which was a Lorentzian of weight 1, of course, and of order and of width gamma. That was just our Friedel virtual bound state level. Now, when we look at u over gamma, say strictly speaking infinity, which would be v equal to 0, right? Which is the singular limit I discussed in the first place. We know that what we should get is a delta function peak centered at minus u over 2 and another delta function peak centered at plus u over 2. These were the removal and addition peak of my isolated atom. What I've shown to you here, just based on local Fermi liquid considerations and the regularity of perturbation theory, is that in between there should always be something here, right? And that this something actually has this remarkable property that if you look at omega equals 0, z completely disappears, as you see from here, and its value is exactly 1 over pi gamma. So there is something here at 0 temperature which is spinned at 1 over pi gamma, the non-interacting, completely independently of interaction, which has a width which is z gamma, which has a total spectral weight which is z. And of course, these guys also exist because they should exist. This is high energy stuff, removing and adding an electron. So there should be here also stuff at order minus u over 2, which has no reason to be so strongly renormalized, so presumably of width gamma, and here the same of width gamma. The total spectral weight has to integrate to 1 because this is a spectral function, but this only concerns z fraction of the spectral weight. And there is complete adiabatic continuity. As you increase u, you gradually narrow this down, transfer spectral weight to this removal and addition peak, and it's only in the singular limit where really gamma vanishes that this so-called Abrikosov-Suhl resonance disappears completely and only the addition and removal peak remain. So this is adiabatic continuity. It's just too bad that in the 60s, people started from this end. That made the problem a lot more difficult. And I think with a slightly different twist, it is Nozière in the 80s who actually sort of pointed out this adiabatic.
Too bad. It was good.
No, it was good. It allowed to invent the RG. That was very good. I agree. In terms of guessing the answer, it was not so great. Right. But in terms of inventing new powerful tools for theoretical physics, it was damn good.
So if you don't have particle symmetry?
Yeah. So if you don't have particle-hole symmetry, then of course these things are no longer centered. There is still a resonance at Well, as we see here, close to 0, not at 0, because this number is not 0, right? But close enough to 0 because z is very small. As long as z is very small, that's close enough to 0. Okay. So you can also ask, you know, these, of course, are the states that correspond to the quasi-particle states of the Fermi liquid. These are high-energy states, removing and adding electrons on my atom. These are the quasi-particle states. So just looking at this, it seems very natural that this scale here is the effective scale below which you have to go to see quasi-particle excitations appearing. Okay? And actually, when you work out everything more quantitatively, using RG ideas, for example, what you can show in this problem is that in the large U over gamma limit, which is the tough limit, not infinity but large, Z is actually exponentially small in U over gamma. So it is something like minus exponential of minus U over gamma with some numbers that I'm not going to write on the board. Okay? So this is an exponentially small scale. This resonance has very, very small weight. This also means that these quasi-particles are relatively fragile, because if you heat up the system above that scale, which controls the Condor temperature of the problem, you kill the quasi-particles, you kill the Fermi liquid, and you kill this resonance. Okay? So now, from this picture, you can immediately understand rigorously the restoration of the 2e square over h conductance. Because if you put this into my transmission conductance formula, where do I want to show this to you? My slides are a little bit scrambled. I need to go back, sorry. Yes, if we, that's not what I want. I want to get back to my conductance formula, which was here. So we had this conductance formula for the conductance, the Meyer-Windgren formula for the transmission conductance, and you see that if I go to 0 temperature, this becomes a delta function. It picks the value of A at 0 frequency. We just showed here without many complicated calculations that in the particle hole symmetric case, this thing is exactly 1 over gamma, right? This 1 over gamma partly compensates this guy, but we have to remember that actually this is only, well, the correct formula is here, because in this problem we have 2 reservoirs, right? So what appears here is this thing here. This is 1 over pi gamma. This gives me 1. Here, this gives me 1/4, and here you get 2e square over h. Okay? So just because, so you can view, if you want, the restoration, the restoration of 2e square over h conductance in 2 ways. The first is with my intuitive argument that you introduce charge states in the ground state wave, different charge fluctuating states in the ground state wave function. That was the qualitative argument. But here you can show it rigorously by showing that this quantity, which plays the role of the transmission coefficient in this interacting Landauer formula, actually is restored to unity at 0 frequency and 0 temperature, which means perfect transmission. Okay, so that's the thing.
If I could just hard report, right? So I would just get spontaneous moment.
Excellent question. Yes, that's a very, very good question. So Hartree-Fock for this problem was done in the same very paper in which Anderson introduced this model. That's what he did. He got half of his Nobel Prize for that. It's a very good year. It's also the year where I was born, 1961. And in that paper, he actually did just the Hartree mean field solution for this. And in the Hartree mean field solution, what you find is that there is a critical value of U where there is polarization of the system into one of the two local moment states. So in Hartree mean field, what you find is that there is a phase transition in this problem. Below a certain critical U, which is of order gamma, okay, you find no local moment. And above a certain critical U, you find that the ground state remains doubly degenerate, up or down. So you can view it in the following way. Let me give you a perspective on that, elaborating on this question. If you work out the effective potential for flipping the moment from that Hartree perspective, you will find that above this fake critical U, there is no critical U in the real solution, right? You will generate a double well potential like this. This is why the Hartree solution gives you a symmetry breaking. But what you should actually do is include all the tunneling processes between these two minima and sum them up. And actually, this is exactly how Anderson, Yuval, and Hamann cooked up an RG for this problem, is by looking at the Coulomb gas of these kinks, anti-kinks processes and understanding how to treat this with RG. It's a formidable set of papers and a formidable development in theoretical physics. So it's really only by summing all these instantons between these two wells that you can understand the physics of the singlet formation, of the Kondo screening, and the buildup of this resonance. Okay? Questions about all these Andersonology? Should really be there is a bunch of people associated to this. You know, there is Kondo, of course, Anderson, Yuval Hamann, Wolf, Nozière, a whole bunch of people. This was one of the central problems in theoretical condensed matter physics between 1960 and 1970. Yes?
You said that the natural part of your
Self-energy.
Was much smaller than gamma.
Yes.
Do you have a physical feeling of what that is?
You have what?
Do you have a physical feeling of what that is?
Yes, because we form these singlets, right? And the conduction electron scatter. We have a gas of quasi-particles that describe the scattering on this singlet, right? And these quasi-particles have very long lifetime. So this omega square you should really think of as the inverse lifetime of these quasi-particles, and it has to be very long. Okay. Yes.
Also, you might want to mention the Toulouse.
Yes.
They found that it scaled the strong couple.
Yes.
They guessed the solution.
Absolutely. Well, as I say, there is I could spend 15 minutes just giving a whole. It's probably time actually to show you this beautiful quotation from Anderson's Nobel lecture, where he said that you'll see here. Let me find the thing. No Hamiltonian so incredibly simple has ever previously done such violence to the literature and to national science budgets. Well, that's attributed to Harry Soule, who is another important name in this field. Okay, so I'm not going to continue very much on this single impurity quantum dot or magnetic impurity framework. I just can tell you a few things before moving to few additional things before moving to DMFT. I mentioned the phase shift, right? I mentioned this thing that here, once we form the singlet, the conduction electron must be phase shifted by pi over 2. So you can ask, you know, in this relatively more modern or more recent setup of a quantum dot, has this been observed? And this was attempted actually in Israel by the groups of Heilblum and Strickmann and others early after the Goldhaber-Gordon et al. Paper. And of course, what you need to set up is some sort of interferometric device to measure this phase shift. And for a very long time, the results were very unclear. But I think very recently, actually about a year and a half ago, there was a beautiful paper, Japanese, French, and German paper, in which finally the controversy was resolved, and soon some two-part interferometric measurement really showed the pi/2 phase shift in the Condor regime, which is what you see here. So I just want to advertise this long history of work revealing the pi/2 phase shift. One other thing I maybe want to tell you about is just the consequence of this pi/2 phase shift and this restoration of a resonance here for the different incarnation of this model, which is scattering of conduction electron of magnetic impurities. So if we put manganese in copper, because there is something really interesting there that I want you to appreciate. So in order to understand that problem, in which we no longer look at the transmission from a reservoir through the dot, but at the scattering of conduction electrons on an impurity, we need, of course, to go back and look at the conduction electron Green's function. Fortunately, in this problem, because it's all Gaussian coupled, I can derive an exact expression that relates the conduction electron Green's function to the local impurity Green's function. And this is relatively easy. I'll let you do that as an exercise. There are various ways to do that, either by functional integral or just inspecting the Feynman rules. And what you will find is this. You will find that GKK prime, observe that this is no longer a translationally invariant problem because we have an impurity. Okay? GKK prime is the bare electron Green's function plus the bare electron Green's function multiplied by Vk, the same one for Vk prime, for K prime, times this. So this is saying that the T matrix for the conduction electrons is exactly proportional to the single electron, the single dot Green's function of the impurity side multiplied by the square of the hybridization. Okay? So what is the consequence for the T matrix of the pi/2 phase shift and the fact that this guy acquires at 0 temperature below and 0 frequency this resonance? Well, you can work this out very easily from this expression. And what you will realize is that the local density of states of my conduction electron now exactly vanishes at 0 frequency. So the way the Condor resonance developed in the D level Green's function is by digging a corresponding hole in the conduction electron Green's function, which just reflects the fact that because of the pi/2 phase shift, there is 0 probability to add an additional electron on that site. But this also is saying that this site should act as an extremely strong scatterer for the conduction electrons. Pi/2 phase shift, in fact, is the maximal possible unitary scattering. So this means that if we now calculate the contribution of this impurity to resistivity for the conduction electrons, we are going to get from this T matrix, just from very simple Kubo, you're going to get this formula. And I've just used the fact, just Kubo, plus the T matrix being proportional to GD. And observe this. This is really remarkable. This is telling you that the contribution of the impurity to the impurity conductivity, because this is 1 over R, involves 1 over the spectral function. While the contribution in transmission through the dot involved to the conductance involve the spectral function in the numerator. Right? Contrast these two formulas. They are remarkably symmetric, except here we have 1 over pi gamma A, and here we have pi gamma E. Okay? So the buildup of the resonance, which allowed perfect conductance in transmission, if you now look at what it means for the scattering of conduction electrons for a physical magnetic impurity, it means maximal possible resistance, right? Which is exactly the Condor phenomenon. So historically, this came way before this, of course. I'm not using chronological time here, okay? So the Condor effect is precisely this. Let me show you perhaps one of the most beautiful set of curves, is the fact that the resistivity of metals that contain a small number of magnetic impurity, instead of having 0 dt positive like normal metals, below some temperature have an upturn of resistivity in which there is an additional contribution to resistivity which makes an increase at low temperature below the Condor temperature, corresponding to what I just described. Yes?
About the Z, shouldn't I think about this as like the number of electrons?
No, you should think of Z as the following thing, okay? If you inject into the system a physical electron from outside, like you would do in photoemission spectroscopy, this physical electron will very quickly disintegrate into a number of excitations. Many of these excitations are high energy, right? And only a small fraction are actually quasi-particle states that live very long because of the omega square. And this small fraction is Z. So it's the fraction of the states that overlap, it's the fraction of the many-body states that overlap with the physical bare electrons. That's how you should think of Z. It's the quasi-particle spectral weight.
Yeah. But so the conductance is still like one conductance constant.
Yes. So Z disappears from the conductance.
That's kind of why
The weight, okay, that's a very good question. It's actually quite a deep question, in fact. The spectral weight that you have in the resonance does not affect the value of the transmission conductance. You could have only one state and still have perfect transmission. It's enough to have one state, which would have Z equals 0, of course, because it's 1 over many. Right? We can discuss this later, but you really only need one state at 0 energy.
it's smaller than one. Right?
Z is smaller than, yeah, but Z, sure.
Okay, so I thought then you have less. That's exactly why I was like, it's less. It looked to me like less than one Fermi quasi-particle mode. So
No. We are talking about extensive, very large numbers here. Z is the fraction of states that with which the physical electron state overlaps, right? But this fraction is macroscopic, it's a huge fraction. What I'm saying is that if you had only one state, in which case Z would be 0 because it's 1 over many, right? You would still have perfect transmission.
Can you say something about the size of the screening cloud?
No. No, because I want to stop talking about single impurities, and I don't know the problem so well. There's a 20-year history there. So, okay. More questions? Okay, good. So now we are going to switch gear, and we are going to use these things in the building up of a theory that allows to describe strong electron correlations for extended systems. And that's dynamical mean field theory. The reason that I took all this detour is that I wanted to familiarize you with the basic building block, which is a zero-dimensional problem with interactions on site. And I probably still have my 45 minutes, right? 40. Okay, good. That will be enough to introduce what I want to introduce. Okay. So now I'm going to introduce you to dynamical mean field theory. And we are no longer going to live in zero-dimensional space. We are going to go back, say, to the Hubbard model, or even to a real solid if we want to. So let me start by reminding you of a few motivations for doing that. We've seen in the introductory part of yesterday's lectures that many materials actually have these metal insulator transitions that are induced by interactions. And in particular, some of them have an odd number of electrons per unit cell, so it makes understanding the insulating state really difficult. One thing I want to drive through your brain is that the insulating nature of this multi-insulator has nothing to do with magnetic ordering. And this is something that Steve also emphasized in his lecture. In a multi-insulator, we have a big scale, which is U, that controls the gap. And the gap is not necessarily as big as U. It depends on how far you are from the mod transition. But definitely, the gap is a high energy scale. And the system is an insulator because of the blocking of charge degrees of freedom. J, the super exchange, which eventually may lead to ordering of the spins, is a much smaller scale. Think about the V203 example that I showed you yesterday. What phases does it have? It has a phase at low pressure, which is a paramagnetic insulator, despite the fact that we have a partially filled shell, with no magnetic ordering and a healthy gap. So it's not going to be we are not going to be able to describe that state of matter by invoking the doubling of the unit cell due to magnetism, which would be a Slater way of generating an insulator, right? Of course, at low temperature, these magnetic moments may eventually order. Usually they do order, except in the exotic spin liquids, okay? But that involves a much lower scale. So one of the purpose we have on our table, one of the duty we have, is to be able to describe a state of matter in which charge is blocked, charge motion is blocked due to the big U, but in which the spins can still fluctuate. So that's a paramagnetic multi-insulator. Okay? Of course, such a state may only exist over some intermediate temperature range.
May I make a comment?
Sure.
So what you're saying is certainly correct, but in the order U, but practice in electric rate, we see some analog of this insulating state without order at temperatures of order J and typically the
Yeah.
So
Sure.
at that point, you have to worry about things like the Leibniz-Lattice theorem, which says that these insulators should have topological order.
Yes.
Theorem. Okay.
Yes. But I also, okay, sure. But as you pointed out, these spin correlations appear at temperature of order J, right? And between J and U, or J in the gap, there can be a very wide energy range, right?
Perfectly okay there, but when we get to is a more difficult issue
Sure.
for the real material, temperatures of the low J.
Absolutely. Well, the correct thing is to we'll discuss this a bit later. Okay, so let me skip some of these things and perhaps go directly into the crux of the matter. So one thing I want to emphasize is that if you look at the photoemission spectrum of multi-insulators, you see features that are very, very simple to understand in terms of excitation of a spectroscopy of individual atoms, and that are very difficult to understand in terms of band structure. So let me show you an example here. So this is the photoemission spectrum of this guy, which is a multi-insulator with one electron on the titanium site in each unit cell. Okay. So if you look at the photoemission spectrum, K integrated, this is what you get. It has a gap, no states at Fermi level. And it has a peak here at about minus 1.5 eV. This peak is extremely simple to understand. It just corresponds to kicking out an electron out of the titanium D shell that contains one electron and kick it out. So this is the D1, D0 transition. People call it a lower Hubbard band, but what it really is just an atomic transition, exactly the same atomic transition I was describing here, D1 goes to D0, broadened by the fact that this titanium atom is not alone. It actually lives in a whole crystal with many other titanium atoms and whatnot. Okay? If you ask somebody to do a band structure calculation of this material, right, what he will produce is this. This is the result of an actual band structure calculation. This is the density of states. So first of all, it's a metal. So we have a slight problem here because this is metallic. Okay? And secondly, well, I cut the graph in an unfortunate place, but there is nothing there, right? So this atomic transition is just not present in this band structure description. Okay? So you could say, okay, well, very simple. This is an insulator, and fine, I can imagine that this insulator is just blocking the charge degrees of freedom on the titanium because of the big U, and what you've seen here is just the atomic transition, and this is true. What happens in a metal when we go to the metallic state? So let's look at the cousin of that guy, which also has one electron in the unit cell, but this time it's a vanadiate compound. So this is strontium VO3, which is a perfectly cubic perovskite, one of the few ones, with one electron, again, in the vanadium D shell. And this is its photoemission spectrum, the dots here. Okay? So what do you see here? Well, you see exactly the same atomic transition. This system is a metal, but it still has quite visible a transition corresponding to removing an electron from the vanadium D shell. But of course, it's a metal, so it has other stuff, right? And the other stuff it has is some low energy states, as should be in a metal, right? Which are the quasi-particles, which build up this density of states here. And this density of states here is abruptly cut at near omega equals 0 because this is photoemission. We only see the whole, like, the negative energy states. But there are also states there in real life, of course. Now, we can also compare this to a band structure calculation. And this is the result of the band structure calculated photoemission spectrum. This is what you get. And so what you see, this is the dashed line. So what you see is two things. First of all, our atomic transition, which was there in the photoemission spectrum, is of course absent in the band structure calculation, which is what I showed you before. But also, the width of these quasi-particle states has been renormalized, in this case, by about a factor of 2. So at least on the occupied side of the quasi-particle excitation, the photoemission bandwidth is about half of what the band structure calculation would tell you, or if you want, loosely speaking, the kinetic energy of electrons has been lowered by a factor of 2, or their effective mass has been increased by a factor of 2. Okay? So what we want is a method to deal with these problems, which is able to capture all these phenomena, capture these atomic transition, capture the formation of these quasi-particle states at low energy, and such phenomena as the increase of the quasi-particle effective mass due to interactions. Yes?
What do you mean by atomic excitation?
Well, it's just you have a D shell of my atom. I remove an electron, right? And I can understand this transition just as an atomic transition. I take an electron from my D shell and I remove it. That's all I mean. Okay? So this is not something you can easily understand in terms of a Bloch band.
Can I understand this plot as the right part comes from the band structure And the left part comes from the interactions.
Well,
If I turn off the interactions, I get only the right part. If I turn off...
no, because if you turn off the good question, to some extent you're right, but if you turn off the interaction, what you will get is the dashed line. Okay? Because you will get essentially, well, this is a very loose language, but you will get essentially this result, right? So the interactions have two manifestations. At high energy, of course, you can think, high energy means very short time scales. So basically, I kick out an electron out of the atomic shell before it has time to wander around. This is why I call it an atomic-like excitation, right? And this is something you can easily understand just from atomic physics, right? This is also, this bandwidth reduction, which was pointed out in the 70s in this context by Brinkman and Rice, is also the effect of interactions. But the effect of interactions on the quasi-particles. That's just saying that the actual quasi-particles of the system are not the bare electrons, right?
Can I then possibly think that interactions redistribute my spectral wave?
Sure. That's what you're going to see in the rest of the lecture, mostly. Okay. Yes. Questions here.
So, shouldn't this behavior threshold just like diverge, like this X-ray problem?
It's not an X-ray problem, because in an X-ray problem, you have no recoil, right? So you just change abruptly the potential. So you would have such a thing if you were looking at core state photoemission. But this is not core state. This is valence state photoemission. And there is recoil. You can talk in this language if you want, yes. But I prefer to view it, which is as the broadening of the atomic transition by the coupling of this atom to the neighboring atoms. Yes?
So this GFT, LJ, do include interactions at some level?
Okay, that I propose to discuss at the end of the lecture because it is a long discussion. It does, yes. The short answer is yes, but not to the extent that these strong correlation phenomena are correctly taken into account. And how to actually do both is a long discussion. Okay, but the short answer is yes. More questions? Okay. Okay, so this is the agenda, right? We want to have a description of solids in which we are able to describe these two kinds of excitations. So we are going to think in terms of atoms. It's no big deal, no big surprise that materials are made of atoms, but usually when you open a solid state theory textbook, only in the first chapter you have atoms, and then chapter 2 has the electron gas until chapter 34, right? So for, you know, I'm not criticizing anything, but for many of us, a solid is an electron gas. Well, what I'm going to tell you here is that if you want to understand at least certain aspects of strongly correlated systems, you should keep the atomic description. So we are going to keep the atomic description at the center of our thinking. That's important, an important point. And then the challenge, of course, will be not to describe these atomic transitions, because this will be simple in this language. It will be to describe eventually the formation of long-lived quasi-particle excitations at low energy. But that challenge we already saw in the context of the zero-dimensional Anderson impurity problem, right? This was the easy part. Understanding that required some work. Okay. So that's what dynamical mean field theory does. And let me describe what dynamical mean field theory is, really. So I'm going to do that for just a simple case, which is just the Hubbard model, our toy model, right? But it can be extended, of course, to the more complex form of interactions and orbital and so on that I described yesterday. So what is the Hubbard model? The Hubbard model you can think of as a single tight binding band plus interactions, but that's not the way I want you to think about. The way I want you to think about is a collection of these single level atoms of the sort we had until now, coupled by electron transfer from one atom to the other. It's just a semantic question, but I really want you to think of this as a collection of my Mickey Mouse atoms coupled by electron hopping. Okay? And so what do we do in statistical mechanics when we have such a lattice problem? First thing we do, before we do more sophisticated things, we actually solve this problem by mean field theory. Mean field theory means we're going to replace this lattice problem by one such entity coupled to an environment. So when we do the Ising model, we replace the whole goddamn problem by one spin which is coupled to the environment by an effective Weiss field. Okay? And this Weiss field H effective is related to the magnetization on the neighbors, right? So can we introduce exactly the same concept in the context of a quantum antibody problem like that? Well, we can. What we have to do is we have to replace this problem by my atom coupled to an environment, which will, of course, be all the rest of the system self-consistently, with which it can exchange electrons. Right? What is this problem? This problem is exactly what I've been talking about for almost 2 hours, namely the single impurity Anderson model. This is my atom, this is my reservoir, and this is the V connection. The only crucial catch is that this reservoir should be made self-consistent. It's no longer given by a physical reservoir. There is no physical reservoir in this problem, right? It should be self-consistently related to describe the rest of the environment. Okay, so how do we set this up? So it is in this context, you know, that this quotation of Shakespeare really makes sense, because he could count himself, even though he's in a nutshell, king of infinite space. That's exactly what we want to do. We want to be king of infinite space while being in a nutshell. Very prophetic. Well, you know the nightmares. You pointed them out many times. That's why I like this thing. Anyhow, so that's the idea. Now you know everything about the Anderson impurity model, right? You know that it's described by this effective action. We've seen this before. That's the part of the effective action that describes the isolated atom. And that's the hybridization term, the V square over I omega n minus epsilon k, that describes the coupling between the environment and the atom. Right? So that will be our local problem. This is what, I'll take your question in a minute, but when we do the Ising model mean field theory, we just replace my complicated lattice problem by an effective local problem, which is H effective times S. This is the H effective times S for this problem. A bit more complicated. It's not just a two-side problem, just two-state problem. It's a real many-body problem of an Anderson impurity type. And this quantity here, the hybridization function that connects my atom to the rest of the system, is the quantum generalization of a Weiss field, if you want. Okay? It's an effective amplitude that allows an electron to leave my atomic site at a certain time, wander around in the rest of the system, of the crystal, and another electron will come back at some other time. And this process is described by this hybridization function, which I do not know yet. I have to determine self-consistently. Yes, there was a question somewhere.
So since your hybridization function is independent of space, so does it mean that it cannot describe any transition symmetry broken state?
Okay, very good question. So this assumption, this description here, as written on the board, only applies because exactly of the point you mentioned, to a phase in which all sites are equivalent. No translational symmetry breaking, also no SU2 spin symmetry breaking, because observe this guy doesn't depend on sigma in my slide. If you want to describe a state that has symmetry breaking, like the antiferromagnet, that would have both SU2 and translational symmetry breaking, you can. You just have to generalize this by saying that this amplitude will depend on sigma and will also depend on whether you are on the A site or the B site. Right? So, for the sake of simplicity, I'm going to write the DMFT equations only for translationally invariant unbroken symmetry state, just for the sake of simplicity. But we can write such equations in any symmetry breaking state allowed through in this approximation. Yes?
So I'm trying to understand which interactions will go into delta.
Okay. So delta is not an interaction term. It's a one-body term, right? But it will depend on the value of u, because there is a self-consistency condition that determines it that I haven't told you yet.
But u appears in the...
Yes, u appears here. In the previous context, where the reservoir was given to us, okay, by the physics of the problem, delta was given to us, and it was something that had nothing to do with u. Now delta is self-consistent. We have to write another equation, which is not on this slide, to determine delta. So for each value of u, and each value of temperature, and each value of doping, and each value of whatnot, delta will take a certain value, which will change with all these parameters. Okay? So it's a single atom problem coupled to a self-consistent bath. And I haven't told you yet how to find delta. I need another equation. Okay. Yes?
It's not a criticism, but isn't it found that usually in SU2 symmetry broken phases, somehow DMFT doesn't correctly recover Goldstone modes?
Yeah, of course, like any mean field theory. So why is DMFT called MFT? Okay? Well, it's partly a misnomer because it should be called dynamical half mean field theory, which is not a very sexy name. Okay? So why half? Because all the spatial fluctuations are frozen. So it has all the usual drawbacks of mean field theory. It doesn't have spin waves and so on, right? That's what you're saying. Why half? Because all the quantum fluctuations in the tau direction, if you want, are all reproduced. So if you want, it's only half of a mean field theory. The full mean field theory, not half, would be freeze both quantum and spatial fluctuation, and that's essentially Hartree mean field, right? Where this guy not only does not depend on the point, but also does not depend on time. It's just a static object. That's really a Weiss mean field then, right? Here it's half of a mean field because we keep local quantum fluctuations, but we kill the spatial fluctuations. Mathematically, you can ask, is this ever controlled? You know, why are you even listening to this? Well, at least there is one limit in which this is exact. And this is the limit where the lattice has large connectivity, or if you live in large dimensions. Then this becomes completely rigorous. What is tau? Okay. Sorry. So I wrote here a way to quantize systems in which you go to a path integral representation and you quantize a Hamiltonian by writing an action in space-time, right? So tau is time, and actually here imaginary time, and it's integrated from 0 to beta, which is 1 over kBt. So this is the standard quantization of a quantum problem by introducing an imaginary time, right? More questions? Good. So I need to tell you how to determine delta. Okay, I can skip this because you already know. Fine. So let me give you a certain point of view on this first. Imagine somebody comes and gives you the exact Green's function on a given site of the Hubbard model. Some really clever guy. Okay? So then you could say, can I represent, so let me call this G local over omega. This is the II Green's function on a given site of, say, the three-dimensional Hubbard model, right? You could say, okay, can I represent this object as the solution of an Anderson impurity problem? Well, yes, you can. You just have to pick the correct delta over omega. So at this point, this is just a statement about representability. Yeah, I have this thing, and I want to represent it as the solution of some Anderson impurity model. I have to choose delta in an appropriate way. Okay, so now we have this Anderson impurity problem with a delta. We can do all the many-body theory I described before, and in particular, this Anderson impurity model will have a self-energy sigma over omega that I've introduced before. And now we are going to, I'll take your question, but I want to first get to the point. We are going to make one key approximation. We are going to declare that the self-energy of my lattice problem, which is of course a function of k and omega, is going to be approximated by a function of omega only, which coincides with that of my Anderson impurity problem. That will be the only approximation I'm going to make. The other thing here is a question of representability. I'm going to choose delta such as to represent correctly the local Green's function from my embedded atom. And the approximation is that the self-energy coincides with the self-energy of the embedded atom. That gives me an additional equation. And I can just close the set of equations now. I'm just going to write that the local Green's function, which because of my representability is equal to the impurity one, should be equal to the sum over k. So here I need a little piece of board. In the lattice problem, the local Green's function is going to be obtained by summing over k the full Green's function, which is something like this. That will be my local Green's function, right? So let me now replace this guy by sigma impurity of omega. That's my approximation. And write that sigma impurity of omega is just the difference between the inverse interacting Green's function and the inverse non-interacting Green's function of my local Anderson impurity problem. So this is G impurity G0 minus 1 minus G impurity minus 1, right? So what was that? This was I omega plus mu minus delta of I omega, and this is minus G impurity minus 1. Take this expression, substitute into this equation, you get this one. So this is telling you that the impurity Green's function, which is a function of delta, if you give me delta, I can solve, in principle, the Anderson impurity model to calculate this quantity, should be related to that same functional by this equation, which knows about my lattice dispersion. Okay? So this is a functional equation which gives me, in principle, delta. And you can check trivial limits. The most trivial one is the isolated atom. This sum over k is, of course, normalized to 1 over the Brillouin zone. Okay? So let's check the isolated atom limit. Obviously, then I should find that delta is 0, because that's the correct way of quantizing my isolated atom. Well, if epsilon k is 0, this is sum over k is irrelevant, gives me 1. And then immediately here from this equation, you find delta equal to 0. Right? So this is trivially correct in the isolated atom limit, collection of individual atoms. Let's now look at the u equals 0 limit, the opposite limit. Right? Well, in the opposite limit, sure enough, this is going to be correct because I've assumed the only assumption I've made is that sigma, it's a big assumption, is that sigma of k and omega is k independent. But at u equals 0, sigma is 0. There is nothing more k independent, right? It's just 0 everywhere. So there was no approximation there. So this was just a way, complicated, bizarre way of representing the non-interacting Green's function from a certain bath. Okay? So this theory by construction is correct when there is no interaction, u equals 0, or when you have a collection of disconnected atoms and you capture all the atomic physics correctly. So, of course, there is no guarantee that it doesn't go berserk in the middle, but it has the two limits correct. Yes?
Is there no way of deriving variational principles in this?
That's a very good question. So there are many different ways of deriving these equations. My favorite one is not actually doing any of this. It's more like doing the cavity method in the spirit of StatMech. And there is also a way of doing what you want to do, namely constructing a functional and minimizing this functional, except that this is a function of omega. So it's never really a minimum. It's usually a saddle point because finite frequency instabilities are not physical instabilities. If your question is, can we show that this is the best local approximation in a certain sense, I'm not sure there is a mathematical proof of that available, even though I believe the answer is yes. But I'm not sure there is a really mathematical proof of that. Okay, so at least is the concept clear? So basically it can be summarized in the following way. We are going to replace the problem by one atom in a bath, and this bath will be self-consistent. This atom in a bath is parametrized by this hybridization function. We need to solve this problem to calculate the local Green's function, but we need to iterate this process because this guy we didn't know in the first place. We need to iterate this process by using this equation, right? Each time we'll get a new G impurity, we can calculate a new delta, and we need to iterate this process until convergence. Yes, Andre.
Just to make a connection to a different approach. I'm going back one slide.
Oops, that was not the right thing to do. Yes.
This one.
Yes.
Just to connect this to Fermi liquid, if I may.
Yes.
In the standard theory of Fermi liquid, you expand around Fermi surface.
Yes.
And then summation over k is density of state times integral d epsilon g.
Yes.
In which case, G local is just sign of frequency up to some number. So can you
Yes.
comment? Then you cannot close the procedure because your local Green function becomes a constant, and there is no dependence of local Green function on the self-energy.
No, but the thing is that this only happens at very low frequency, right?
Right. This is what I'm
So, yeah. So these equations couple low and high frequencies.
But can you reproduce conventional Fermi?
Of course, of course. Well, it's very simple. At low well, okay. So it all depends on delta of omega, right? If delta of omega has finite spectral weight at low frequency, then we have a local Anderson impurity which is coupled to a bath that has states at low frequency, and we have all the local Fermi liquid theory I described before, right? And I'll show you results for the self-energy that have very clearly low frequency Fermi liquid behavior, right? If delta of omega, on the other hand, has no states at low energy, then I have the problem of a local impurity model, local impurity problem, in a bath that has no states, and that's not a Fermi liquid, that's a state with a gap, right? And that's precisely how the mod transition works, as you, well, we'll see tomorrow, probably, or later today in the tutorial. That's how the mod transition work in this framework, namely that having self-consistently delta of omega go from gapless state to a gapped state.
Right. The question, if I make the question I'm asking for, we have a local Fermi liquid, which is
Yes.
ideal to consider mod transition. How this local Fermi liquid, which is related to what we call a conventional Fermi liquid, when everything comes from the states near the Fermi surface, and you don't need to go beyond linearization.
But that's the same thing. We've integrated out all the spatial degrees of freedom, right? So the low frequency, low K expansion of my self energy, right, is completely conventional, except there is no K minus Kf square.
Sure.
There is just omega square.
No, no, but, sorry. In your theory, sigma impurity omega goes to finite values.
No, no, absolutely not. Goes to omega square. Imaginary part is omega square. No, it's delta. That's no. Im sigma. Okay, so now let me jump to the relevant slide. I need to skip a lot of things. And let me show you, because they are asking how these things behave. That's the metallic state in this theory, right? The imaginary part of sigma behaves as Fermi liquid theory should tell you it should behave, right? As we saw before. If we have an Anderson impurity model coupled to a reservoir that has states at low energy, Im sigma of omega behaves like omega square. Of course, the width of the level is not Im sigma of omega. It's Im delta corrected by Im sigma. This is the thing you have in mind, right? But the quasi-particle scattering is Im sigma and is omega square.
That's also strange, because that's only true at K equals KF, not just K away from it.
Well, here it's true at K away from Kf because there is no K dependence, right? Going to the Fermi energy means going to omega equals 0.
But, sorry, I don't want to disturb your, so if you want to finish, I just want to ask. So, in answer, more specific question I want to ask is this. If you take conventional Fermi liquid theory,
Yeah.
for example,
This is conventional Fermi liquid theory, except in large dimensions.
right.
That's all there is to
This
it.
is the answer. Because we also know that, for example, if you are in 2 dimensions at 0 temperature, it's not omega square, it's omega square log.
Sure,
And
here it's purely
this
omega
is
square.
out.
Yeah, because it's large D. Yeah. Yeah. It's omega square above, anyway, it would be omega square above 2 dimensions, right? This is much above 2 dimensions. So, yeah. So just to complete Subir's question, but here I'm not following the logical order. Okay, this is now a numerical calculation of the self-energy in the metallic state. But we are skipping 25 slides here, but just to answer his question, okay? So this is using something which is called the Wilson numerical normalization group. So what you see here is an omega square self-energy. It's a beautiful omega square. You can actually check that, which lives in a very, very tiny energy range here, right? And this defines the place where Landau quasi-particles exist. So this theory, because it matches high and low energy scales, is not only able to tell you what is the physics of the quasi-particle at low energy, but what you have to do to break the quasi-particles. And it allows you to define the scale where things deviate from Fermi liquid. So this is your omega square, right? But many other things happen here, which allow in particular to describe how the quasi-particles are destroyed as we move in temperature and we cross over from Fermi liquid to bad metal, which hopefully I will attain in lecture 6 or something. Okay, similarly, if you are interested in the real part of self-energy, what you see here is the linear in omega regime of the Fermi liquid. And you see here, that will give me my effective mass. Okay? And you see here how, as you go away from the Fermi liquid, quasi-particles unrenormalize gradually because this slope goes to a lower value. So here you see strongly dressed quasi-particles, and as you move away from low energy, they undress a little bit. Okay? But all this will come later. I think I have to stop there, right?